In analytic geometry, an asymptote of a curve is a line such that the distance between the curve and the line approaches zero as they tend to infinity. Some sources include the requirement that the curve may not cross the line infinitely often, but this is unusual for modern authors. In some contexts, such as algebraic geometry, an asymptote is defined as a line which is tangent to a curve at infinity. The word asymptote is derived from the Greek a1/4 I florin I1/4 I euro I permil I, which means not falling together, from a1/4 priv. Plus I florin I 1/2 together plus I euro I permil I fallen. The term was introduced by Apollonius of Perga in his work on conic sections, but in contrast to its modern meaning, he used it to mean any line that does not intersect the given curve. There are potentially three kinds of asymptotes: horizontal, vertical and oblique asymptotes. For curves given by the graph of a function y equals e, x, horizontal asymptotes are horizontal lines that the graph of the function approaches as x tends to plus a or a. Vertical asymptotes are vertical lines near which the function grows without bound. More generally, one curve is a linear asymptote of another if the distance between the two curves tends to zero as they tend to infinity, although usually the term asymptote by itself is reserved for linear asymptotes. Asymptotes convey information about the behavior of curves in the large, and determining the asymptotes of a function is an important step in sketching its graph. The study of asymptotes of functions, construed in a broad sense, forms a part of the subject of asymptotic analysis. Introduction. The idea that a curve may come arbitrarily close to a line without actually becoming the same may seem to counter everyday experience. The representations of a line and a curve as marks on a piece of paper or as pixels on a computer screen have a positive width. So if they were to be extended far enough they would seem to merge, at least as far as the eye could discern. But these are physical representations of the corresponding mathematical entities. The line and the curve are idealized concepts whose width is zero. Therefore the understanding of the idea of an asymptote requires an effort of reason rather than experience. Consider the graph of the function shown to the right. The coordinates of the points on the curve are of the form where x is a number other than zero. For example, the graph contains the points. As the values have become larger and larger, say 100, 1000, 10,000. Putting them far to the right of the illustration, the corresponding values of 0.01, 0.001, 0.0001 become infinitesimal relative to the scale shown. But no matter how large becomes, its reciprocal is never zero, so the curve never actually touches the x-axis. Similarly, as the values have become smaller and smaller, say 0.01, 0.001, 0.0001, making them infinitesimal relative to the scale shown, the corresponding values of 100, 1000, 10,000 become larger and larger. So the curve extends farther and farther upward as it comes closer and closer to the y-axis. Thus, both the x and y-axis are asymptotes of the curve. These ideas are part of the basis of concept of a limit in mathematics, and this connection is explained more fully below. Asymptotes of functions. The asymptotes most commonly encountered in the study of calculus are of curves of the form y equals e, x. These can be computed using limits and classified into horizontal, vertical and oblique asymptotes depending on its orientation. Horizontal asymptotes are horizontal lines that the graph of the function approaches as x tends to plus a or a. As the name indicate, they are parallel to the x-axis. Vertical asymptotes are vertical lines near which the function grows without bound. Oblique asymptotes are diagonal lines so that the difference between the curve and the line approaches zero as x tends to plus a or a. More general type of asymptotes can be defined in this case. Only open curves that have some infinite branch can have an asymptote. No closed curve can have an asymptote. Vertical asymptotes. The line x equals a is a vertical asymptote of the graph of the function y equals e, x, if at least one of the following statements is true. The function e, x, may or may not be defined at a, and its precise value at the point x equals a does not affect the asymptote. For example, for the function has a limit of plus a as x a 0 plus e x has the vertical asymptote x equals 0, even though e 0 a equals a 5. The graph of this function does intersect the vertical asymptote once, at. It is impossible for the graph of a function to intersect a vertical asymptote in more than one point. Moreover, if a function is continuous at each point where it is defined, it is impossible that its graph does intersect any vertical asymptote. A common example of a vertical asymptote is the case of a rational function at a point x such that the denominator is 0 and the numerator is non-zero. Horizontal asymptotes. Horizontal asymptotes are horizontal lines that the graph of the function approaches as x a plus or minus a. The horizontal line y equals ac is a horizontal asymptote of the function y equals e, x, if, or. In the first case, e, x, has y equals ac as asymptote when x tends to aa, and in the second that e, x, has y equals ac as an asymptote as x tends to plus a. For example, the arctangent function satisfies, and, so the line y equals ai /2 is a horizontal tangent for the arctangent when x tends to aa, and y equals I /2 is a horizontal tangent for the arctangent when x tends to plus a. Functions may lack horizontal asymptotes on either or both sides, or may have one horizontal asymptote that is the same in both directions. For example, the function e, x, equals 1/x2 plus 1, has a horizontal asymptote at y equals a0 when x tends both to aa and plus a because, respectively. Oblique asymptotes. When a linear asymptote is not parallel to the x or y axis, it is called an oblique asymptote or slant asymptote. A function f, x, is asymptotic to the straight line y equals mx plus n if. In the first case the line y equals mx plus n is an oblique asymptote of e, x, when x tends to plus a, and in the second case the line y equals mx plus n is an oblique asymptote of e, x, when x tends to a. An example is e, x, a equals ax plus 1/x, which has the oblique asymptote y equals ax as seen in the limits. Elementary methods for identifying asymptotes. The asymptotes of many elementary functions can be found without the explicit use of limits. General computation of oblique asymptotes for functions. The oblique asymptote, for the function f, x, will be given by the equation y equals mx plus n. The value for m is computed first and is given by where a is either or depending on the case being studied. It is good practice to treat the two cases separately. If this limit doesn't exist then there is no oblique asymptote in that direction. Having m then the value for n can be computed by where a should be the same value used before. If this limit fails to exist then there is no oblique asymptote in that direction, even should the limit defining m exist. Otherwise y equals mx plus n is the oblique asymptote of e, x, as x tends to a. For example, the function e, x, equals /x has, an n. So that y equals 2x plus 3 is the asymptote of e, x, when x tends to plus a. The function e, x, equals ln x has, and then, which does not exist. So y equals ln x does not have an asymptote when x tends to plus a. Asymptotes for rational functions. A rational function has at most one horizontal asymptote or oblique asymptote, and possibly many vertical asymptotes. The degree of the numerator and degree of the denominator determine whether or not there are any horizontal or oblique asymptotes. The cases are tabulated below, where deg, numerator, is the degree of the numerator, and deg, denominator, is the degree of the denominator. The vertical asymptotes occur only when the denominator is 0. For example, the following function has vertical asymptotes at x equals 0, and x equals 1, but not at x equals 2. Oblique asymptotes are rational functions. When the numerator of a rational function has degree exactly 1 greater than the denominator, the function has an oblique asymptote. The asymptote is the polynomial term after dividing the numerator and denominator. This phenomenon occurs because when dividing the fraction, there will be a linear term, and a remainder. For example, consider the function shown to the right. as the value of x increases, f approaches the asymptote y equals x. This is because the other term, y equals 1/x plus 1, becomes smaller. If the degree of the numerator is more than 1 larger than the degree of the denominator, and the denominator does not divide the numerator, there will be a non-zero remainder that goes to 0 as x increases, but the quotient will not be linear, and the function does not have an oblique asymptote. Transformations of known functions: if a known function has an asymptote equals x, then the translations of it also have an asymptote. If x equals a is a vertical asymptote of f, x, then x equals a plus h is a vertical asymptote of f, x h. If y equals c is a horizontal asymptote of f, x, then y equals c plus k is a horizontal asymptote of f, x, plus k. If a known function has an asymptote, then the scaling of the function also have an asymptote. If y equals ax plus b is an asymptote of f, x, then y equals cax plus cb is an asymptote of cf, x. For example, f, x, equals x1 plus 2 has horizontal asymptote y equals 0 plus 2 equals 2, and no vertical or oblique asymptotes. General definition. Let ℝ2 be a parametric plane curve, in coordinates a, t, a equals a, x, t, y, t. Suppose that the curve tends to infinity, that is, a line A is an asymptote of a if the distance from the point A, t, to a tends to 0 as ℝ_a_b. For example, the upper right branch of the curve y equals a1/x can be defined parametrically as za equals at, y equals a1 per ton. First, za aaa as ℝ_aaa and the distance from the curve to the x-axis is 1 per ton, which approaches 0 as ℝ_aaa. Therefore the x-axis is an asymptote of the curve. Also, yaaa as ℝ_aa0 from the right, and the distance between the curve and the y-axis is t, which approaches 0 as ℝ_aa0. So the y-axis is also an asymptote. A similar argument shows that the lower left branch of the curve also has the same two lines as asymptotes. Although the definition here uses a parameterization of the curve, the notion of asymptote does not depend on the parameterization. In fact, if the equation of the line is then the distance from the point A, t, a equals a, x, t, y, t to the line is given by if I cubed, t, is a change of parameterization, then the distance becomes, which tends to 0 simultaneously as the previous expression. An important case is when the curve is the graph of a real function. The graph of the function y equals a, x, is the set of points of the plane with coordinates. For this, a parameterization is. This parameterization is to be considered over the open intervals, where a can be a and b can be plus a. An asymptote can be either vertical or non-vertical. In the first case its equation is za equals ac, for some real number c. The non-vertical case has equation y equals mx plus n, where m and are real numbers. All three types of asymptotes can be present at the same time in specific examples. Unlike asymptotes for curves that are graphs of functions, a general curve may have more than two non-vertical asymptotes, and may cross its vertical asymptotes more than once. Curvilinear asymptotes. Let ℝ2 be a parametric plane curve, in coordinates a, t, a equals a, x, t, y, t, and b be another curve. Suppose, as before, that the curve a tends to infinity. The curve b is a curvilinear asymptote of a if the shortest of the distance from the point a, t, to a point on b tends to 0 as ℝ_a_b. Sometimes b is simply referred to as an asymptote of a, when there is no risk of confusion with linear asymptotes. For example, the function has a curvilinear asymptote y equals x2 plus 2x plus 3, which is known as a parabolic asymptote because it is a parabola rather than a straight line. Asymptotes and curve sketching. The notion of asymptote is related to procedures of curve sketching. An asymptote serves as a guideline that serves to show the behavior of the curve towards infinity. In order to get better approximations of the curve, asymptotes that are general curves have also been used, although the term asymptotic curve seems to be preferred. Algebraic curves. The asymptotes of an algebraic curve and the affine plane are the lines that are tangent to the projectivized curve through a point at infinity. For example, one may identify the asymptotes to the unit hyperbola in this manner. Asymptotes are often considered only for real curves, although they also make sense when defined in this way for curves over an arbitrary field. A plane curve of degree n intersects its asymptote at most at two other points, by bar copyright Zout's theorem, as the intersection at infinity is of multiplicity at least 2. For a conic, there are a pair of lines that do not intersect the conic at any complex point. These are the two asymptotes of the conic. A plane algebraic curve is defined by an equation of the form p, x, y, a equals a0 where p is a polynomial of degree n. Where pk is homogeneous of degree k. Vanishing of the linear factors of the highest degree term Pn defines the asymptotes of the curve, setting Q equals Pn, if Pn, x, y, equals Qna1, x, y, then the line is an asymptote if and are not both 0. If and, there is no asymptote, but the curve has a branch that looks like a branch of parabola. Such a branch is said a parabolic branch, even when it does not has any parabola that is a curvilinear asymptote. If the curve has a singular point at infinity which may have several asymptotes or parabolic branches. Over the complex numbers, Pn splits into linear factors, each of which defines an asymptote. 0 over the reals, Pn splits in factors that are linear or quadratic factors. Only the linear factors correspond to infinite branches of the curve, but if a linear factor has multiplicity greater than 1, the curve may have several asymptotes or parabolic branches. It may also occur that such a multiple linear factor corresponds to two complex conjugate branches, and does not correspond to any infinite branch of the real curve. For example, the curve x4 plus y2 minus 1 equals 0 has no real points outside the square, but its highest order term gives the linear factor x with multiplicity 4, leading to the unique asymptote x equals 0. Asymptotic cone. More generally, let us consider a surface that has an implicit equation where there are homogeneous polynomials of degree and. Then the equation defines a cone which is centered at the origin. It is called asymptotic cone, because the distance to the cone of a point of the surface tends to 0 when the point on the surface tends to infinity. See also, asymptotic analysis, asymptotic curve, big O notation, references, general references, Kuptsov, L.P., Asymptote, in Haswinkel, Mikhail, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Specific references. External links, Asymptote at planetmath.org. Hyperboloid and asymptotic cone, string surface model, 1872 from the Science Museum.